Okay, welcome. We'll get started here in just a second. We're going to finish up here, chapter 15, I think. And then we're going to roll into chapter 16. Those notes are up on our Canvas site again if you need them. And, we'll get going on that. So, again, we'll give everybody just a second here before we get started. Find some stuff here. Maybe a calculator would be good. Let's see. All right. Maybe. We'll see. All right. So we are actually right in the middle of a titration problem, which hopefully you took the time between last lecture and this lecture to complete the last couple of parts. We started working on it last time. And we were finishing up pretty much talking about titration calculations. And remember that when we do titrations, it's super important to understand where you are in terms of the titration curve, because that gives you a tremendous amount of information actually going into the calculation as to what type of calculation you should be kind of doing. So as I mentioned before, a lot of times people do run into problems with these calculations because, for lack of sort of a better word there, they just sort of jump right into it, and they really don't take just a moment or two to think about what type of titration are you dealing with, where you are in that titration curve. Because like I said before, pretty much if you know the type of titration and you know where you are in that curve before you actually do any calculation, you should have a pretty good understanding of A, the type of calculation you should be doing, and B, in terms of the pH, what type of pH you should be getting. You should understand actually before you do the calculation that, hey, I'm before the equivalence point, probably should be acidic, or I'm after the equivalence point, maybe it should be basic. I'm at the equivalence point exactly, it should be basic, or it should be acidic, depending on the type of titration that you're doing and the calculation that you do. So again, it's really helpful for a lot of people to really sort of visualize almost the curve, if you will, and where you're at. Because like I said, right out from the gate there, you should have an understanding as to sort of where you should be going. And that obviously helps a lot of people not get lost. Again, a lot of people do get sort of lost along the way because they just sort of jump into it and just like, I'm not really sure what's going on. But again, I got a couple of numbers. I know this formula uses a couple of numbers. Why not just toss it in there and hope for the best? So I would highly recommend that, you take some time, you understand, we really talked about 4 distinct parts in all those different titration curves and sort of what's going on at those points, and sort of have that understanding of what is happening at that point in the titration. Now, we are in the middle of this one here, which, to remind everybody, was a titration of a weak acid, so HNO2, with a strong base, which is sodium hydroxide. And here we are adding the sodium hydroxide to the weak acid. And in this case, we did the first part of the calculation, which was before we started the titration. So again, before we started the titration, the only thing that we had in the flask or the beaker is a weak acid, which means, again, knowing that that's a weak acid and knowing we haven't added anything, that should automatically in your head ring to you, like we did, that this is really just a Ka type problem. So it's just a simple Ka problem with an ice table with molarity, because we haven't added anything. We solve for X. X is the H plus concentration, which then could go into our pH equation. And then obviously we could get our answer like we did in part A. And I think we opened up with 2 point something, if I'm not mistaken. Then we started adding, which was 80 milliliters, which is where we sort of finished up talking about last time here. And remember that once we add, obviously we're adding volume. So we do definitely need an ice table. And more importantly, again, that ice table should be done in moles. We also can see once we got into our ice table, if you did not know it from the problem, which you probably should, because the next question is what's the pH at the equivalence point. But if you didn't have that part from our ice table, again, we could see that what we are adding, which is our sodium hydroxide here, is less moles than what we started with, which was our weak acid. And whenever you're adding less moles than what you start with in a titration, that means that you're definitely before the equivalence point, which also in your head in this type of titration should signal that you're in the buffer region, which means I know when I'm done with my first ice table, just like we were here, I should end up with a buffer. And that's the things that you want to sort of think about. And you can see when we did our ice table here and our problem, that's exactly what we ended up with. We ended up with HNO2 and NaNO2, which is a weak acid, and its conjugate base, which is a buffer. So again, if you sort of have that in your head, you have sort of a game plan as to what you should do. And obviously at that point, we went into the Henderson-Hasselbalch equation and was able to get the pH, which is 3.95. So I think we started at 2 and some change, maybe high 2s, and we added some base, and now we're at 3.95 in terms of our titration. So we are at least going in the right direction since we are adding base in this case. The key with titrations is it really is all the calculations that you know how to do. The problem is people don't know where they're at and what calculation they should be doing. So again, that's why it's really important to understand the conceptual part of what's going on so that you do the right math. So at this point here, we're going to be at part C, which is the equivalence point. And so we will continue on with part C of this calculation. And I'm going to try to remember everything we had going on here. That's the Ka value there, 4.5 to the minus 4. So part C, let's take a look and see how we did, hopefully. So in part C, it's at the equivalence point. And again, here we are starting with 100 milliliters, I think, right? The 0.1. So we have 100 milliliters of the 0.1 molar nitrous acid, Ka value, just to remind me, 4.5 to the minus 4. And we want to know what is the pH when we're at the equivalence point. And again, we're adding 0.1 molar sodium hydroxide. So in this particular problem, they didn't straight out tell you what the volume was to reach the equivalence point. So there really is a couple ways you could figure it out. And we'll just talk about 2 ways that you could sort of figure it out. Again, we've seen this reaction in the first 2 parts, which is our HNO2 plus our sodium hydroxide. Going to give us our NaNO2 and our water. Now, we've seen that it is a 1-to-1 relationship. So whenever it's a 1-to-1 relationship and you want to figure out how much to reach the equivalence point, you actually can do a little M1V1 equals M2V2 if you want to figure out the volume. M1 in this case would be 0.1. V1 would be 100 divided by M2, which is 0.1, tells us to reach the equivalence point, if you solve for V2, you would need 100 milliliters to get there. Reminder that if it's not a 1-to-1 relationship, you should never use M1V1 equals M2V2 because you will not have the right mole-to-mole relationship. Technically speaking, it only works because the stoichiometry of it is 1-to-1. So if it's not a 1-to-1 relationship, you would have to kind of do a little stoichiometry problem to help you figure that out. Now, another way you could get to, I need to add 100 milliliters to get to the equivalence point of the base, is you could just use your ice table to kind of help you a little bit. So let's see how that will work. So initially here, just like we did in the other steps, we're going to figure out the moles of our HNO2, right? 0.1 for the 100 milliliters times 0.1 gives us 0.01 moles. So you may say, well, how does that help me? How it helps you is you should know that if we're at the equivalence point, the moles of our sodium hydroxide, which is what we're adding, should be exactly equal to the moles of our nitrous acid, which is what we started with. Which means, without really doing a calculation, you probably could pretty safely know you should have 0.01 moles of your sodium hydroxide. And you may still say, well, how does that help me get to the volume that I would need? How that would help you get to the volume is, you know that the molarity is moles per liter. So we just figured out that we need 0.01 moles to reach the equivalence point. We have the molarity that is 0.1. We could take the liters would equal the moles divided by the molarity. And if you do that, you will get 0.1 liters, which is 100 milliliters. So you could actually work backwards using the moles of the sodium hydroxide in this case and the molarity that's given to you to figure out the actual volume that would be needed to reach the equivalence point. Again, because it's a one-to-one relationship, you could also use really the dilution equation to get you there. So again, there's a number of different ways you could figure it out. And it's very common in a lot of problems that they may not just straight out say, you know, you added 100 milliliters to get to the equivalence point or anything like that. So we will continue on with our table here. That would be 0. So at this point, since we are at the equivalence point, you really can't pick the wrong number since there's only one number. So the change here has to be 0.01, 0.01, and plus 0.01. Which means when we reach equilibrium, as we would expect, all of our weak acid is gone, all of our strong base is gone, and we have 0.01 moles of our sodium nitrite. And this is why it's important to figure out the total volume at this point. So the total volume at this point is the 100 we started with and the 100 that we needed to reach the equivalence point, which would be 200 milliliters. So again, you do usually need to figure out the volume because you need to now convert this back to molarity, which would be 0.2 liters, right? Gives you 0.05 molar. 0.05 molar. Any questions on that ice table there? So again, at this point, if you have a true understanding of what's happening here in our titration, you should know that I am at the equivalence point in a weak acid, strong base titration, which means I need to, as we talked about, do not just one ice table, but I need to do 2 ice tables because I will have a salt that is left over. And part of the salt, which specifically is the NO2 minus, came from a weak acid, which means it is relatively strong. And as I already know going into this problem, I need to do a hydrolysis problem. I also should know going into this problem that it should end up being basic because I already know all these things before I even picked up the pen to do this problem because I understand where I'm at and what type of titration it is. So the next will be our hydrolysis reaction of NO2 minus plus some water. And again, the NO2 minus came from a weak acid, which means it's going to act as a conjugate base. And by the way, it doesn't have an H to give, so it could only accept it, right? Logic is not a bad thing to think about, right? And we're going to get HNO2, which is always what you get where it comes from. And we'll get a little hydroxide. And this is also why we know without doing a calculation that this should be basic at this point. Now, our initial amount for this table will be our equilibrium amount that we got here. So initially 0.05, 0, and 0. Change, and remember this table will now be x's. And that means at equilibrium 0.05 minus x, x, and x. Any questions on the second table? At this point, we're going to go into our K expression, which is our products over our reactants. And the other important thing you should know is I see OH minus here, which means this should be KB. So again, we were not given KB. We were given the Ka value. So this is where we have to use the Kw to convert it. And I'm going to do that. So you're going to take Kw, which is 1 to the minus 14. We're going to divide it by 4.5 to the minus 4. That's going to give us 2.2 to the minus 11. And again, I'll just write it here how I got that because I'm running out a little bit of room here, but our KB would equal KW times KA. So again, we use that relationship there to get that 2.2 times 10 to the minus 11. At this point, we can plug everybody in. We're going to do x squared over 0.05 minus x equals 2.2 times 10 to the minus 11. We're going to assume that x is equal to 0, which means we're going to take 0.05 times it by our KB. We're going to take the square root of it, and we're going to get a number, some type of number. We'll call it 1.05 to the minus 6, just to keep a few digits. And we do want to check it, so we'll divide that by 0.05. We'll times it by 100, and I think you're at like 0.002%, which means the check was all good here. That does mean now that if we go into our table, flip the page, if we go into our table for part C, we have an x value that equals, I guess I shouldn't erase that, 1.05 to the minus 6. And that equals from our table the OH minus concentration, which means we could calculate again, not the pH, but the POH. And the POH would be minus the log of 1.05 times 10 to the minus 6, going to give us 5.98. And that will then give us a pH that is 8.02. And again, that pH does make sense based on when we started the problem. We know that in this type of titration, once you reach the equivalence point, you should have a basic pH. Any questions on any of those steps, where any numbers came from? Did I make it up? Probably. Any questions on any of that? So hopefully you did part C, and hopefully you got to that answer. And again, if you understand what is happening before you get there, you should have a pretty good idea as to sort of where you should be going. All right, then we have one more part of this problem left, which is part D. And in part D, we want to know what is the pH after we've added 105 milliliters of the base. So we'll just pick up part D here. So part D is 105 milliliters of the sodium hydroxide, which again is 0.1 molar, added to 100 milliliters of our 0.1 molar HNO2. So obviously at this point, we're going to kind of start it the exact same way. We're going to take our HNO2, our sodium hydroxide, a little sodium nitrite, and our water. And like normal and how we started all the other three, or the other two at least, we're going to convert everybody into moles. So 0.1 liters times 0.1 molar gives us our same starting moles for our HNO2, which is 0.01, again in moles. Now we're going to take 0.105, which is the 105 milliliters, times 0.1, gives us 0.0105 for our sodium hydroxide, and 0. Now, if you weren't doing a problem where you had all these parts given to you, again, if you're not sure where you're at, you can use your ice table to help you. And what we see is at this point in this titration, what we are adding is more moles than what we started with, which would tell us that we have definitely gone past the equivalence point. So again, if you don't have that information given to you, you're not sure where you're at, you should know that you are definitely past the equivalence point, which also means you should know that at this point in the titration, you're just dumping in some base, right? So you got some excess base. And because you have excess base, like we talked about a number of times, there is a switch. And in this case, the nitrous acid is actually the limiting reagent and going to be used up. So our change would be 0.01 minus 0.01 and plus 0.01, which means at equilibrium, you got none of that guy. I am going to grab my calculator. Let's see here. That's 0.01. So make sure I don't miss any zeros, I hope. All right, 3 zeros and a 5 looks like a winner in that case. 3 zeros and a 5 moles and 0.01 moles of this guy. At this point, just like we've done before, we do want to convert back into molarity. As we talked about, moles in the first table, just convert it back to molarity at the end. You won't run into too many troubles if you just kind of automatically do that. Total volume at this point is we had 100 milliliters to start with. We added 105. So that is 205 milliliters as our total. So we'll divide this guy by 0.205 liters. We'll divide this guy by 0.205 liters. And we will end up with 0.00244, we'll call it. And for our other one, we will end up with 0.0488. So again, if you're really not sure what's going on, look at your table. And again, we see at this point, we do have sodium hydroxide left over. We do have some sodium nitrite left over. And as we saw before, this is not a buffer. They are not related to each other. But we did see that this guy would affect the pH. And it will go through hydrolysis and act as a base. But more importantly, at this point in the titration, we have sodium hydroxide left, which is a strong base. And out of the two, the sodium hydroxide, again, just needs to go for a swim, and then it will break apart into hydroxide. The NO2 minus got to go find some water and stuff and do a little reaction. So out of the two, and at this point in the titration, we ignore the contribution of the salt, and we could just use the sodium hydroxide to figure out the pH. And because sodium hydroxide is a strong base, that means that this concentration is actually our hydroxide concentration. And that means that we could then get the POH would equal minus the log of 0.00244. And gives us a POH of like 2.61. Then that means our pH is 14 minus 2.61. And that looks like 1139, which is definitely basic. And what we would sort of expect at this point in the titration, because we are just dumping sodium hydroxide in there. So the question is, again, why at this point in the titration do we sort of ignore the contribution of the sodium nitrite and just look at the hydroxide concentration? So it's sort of a simple sort of idea, which is you do have both of those things in there. So you do obviously have the NO2 minus, which then could go find some water, do a little reaction, right? And, you know, it could generate, like we talked about there, this and some OH minus. So in order for this to happen, and remember, this is sort of a weak reaction that's happening, which means for the most part, it's, you know, on this side, but it will produce a little of these guys, right? And that's different than what we also have in there at that point, which is sodium hydroxide, which once it goes for a swim is going to 100% break apart into these ions, which means when you're comparing the two, because sodium hydroxide is a strong base, it is going to be probably the major contributor of hydroxide in that solution at that point. Again, the NO2 minus got to do a reaction. It's sort of a weak reversible type reaction, which means in comparison, it is going to be producing some, but it's probably not as much or not the major source of hydroxide, because that's going to come from the sodium hydroxide, which you were just dropping in. So every time you do a drop of that sodium hydroxide past the equivalence point, because it has no HNO2 really to react with, it's just going to break apart, and you're just constantly generating lots and lots of hydroxide really quick. And that's why, again, you see that jump, right, in terms of the pH. And that's why it's the major contributor, because it doesn't have to go find water or do a reaction, and that reaction that's being done is a weak acid or a weak sort of base reaction. So remember, although NO2 minus is considered a strong conjugate base, it is strong in the sense of weak, and it is definitely much weaker than any just straight out strong base that would be present. Yeah, so essentially, if you probably did the calculation, almost like probably like when we were doing the diprotic acid, for example, right? We saw that the majority of the H plus in a diprotic acid came off from that first H plus. And in reality, if you sort of did the calculation, there was H plus that came off in the second one that came off, and there was some H plus that came off in the third one that came off in that H3PO4. But as we saw, when you added that back to the original amount of H plus that came off, the number really didn't change. So as you said, you know, it is definitely contributing, but it's not definitely the major contributor at this point. And that's different than the step before, because in the step before, we're at here, in this step before where we did look at its contribution, you could see at that point, there is no strong base left, which means the salt itself is the major contributor at that point, because you don't have any strong base there at that point. But in this case, because we do have the strong base, it's not going to be the major contributor. And that's why we do look at it at the equivalence point, because out of everything that's there at the equivalence point, the only thing that's really going to be generating some, you know, OH minus, for example, and stuff like that, is that salt that's there. And then when we get past the equivalence point, you now pretty much have that strong basis being added in. Other questions on that? Or questions on titration problems or how to do titration problems? Obviously, you do need to be able to do titration problems like we talked about. You do need to be able to, excuse me, you do need to be able to, what did I say, titration problems, know the three different types of titrations we talked about, the curves, and obviously be able to calculate anywhere along, you know, that titration curve, or the entire titration curve. We'll just have one question on the exam. Give me the pH all the way through. I'm kidding, by the way. It will not be that. Any questions on any of that? Okay, so let's talk then about, to finish up this chapter, indicators and acid-base indicators. And obviously, when we do titrations, we do use indicators to help us sort of visualize usually the equivalence point. And what we're looking for in terms of an indicator is one where we would expect it to change color near the equivalence point. And we do want to be able to sort of see a distinct color change occur as we get to that equivalence point. Why do we want to kind of see that color? We want to see that color so we know to literally shut the burette, right, and stop our titration. Unlike the titrations we're going to see today, usually when you do the titrations, you usually want to stop right at that equivalence point. And again, that's the point where we have equal amounts of acid and base in terms of the moles. So what are indicators? Indicators are essentially weak acids, and that's why you could kind of see it written almost like a weak acid. The IN just stands for an indicator, and the H means that it's protonated. So it's got like an extra H plus on it, kind of like an acid. And just like a weak acid, when it breaks apart, it will break apart into H plus, and the deprotonated or unionized version, the IN minus, which again just stands for the indicator that has lost an H plus. And depending on the ratio of the protonated form of the indicator to the non-protonated form of the indicator, as to what color we will kind of see. So if the HIN, which is the protonated form, over the IN minus is greater than or equal to 10, typically we will be able to see the color in acidic solution, or whatever color it is in acidic solution. And vice versa. If it's less than that, we will see sort of the base color. So as you can see on here, it might be a little hard to see, but they work over a pH range. So for example, like I may have talked about a little bit before, our very popular one, which is phenolphthalein, which is right about here. So our phenolphthalein, for example, works like 8.3-ish to like 10 in terms of pH. And again, at around 8.3, it's almost colorless. And then it just gradually gets that pink color. Imagine it's pink, not purple. Right? And then obviously as you get closer to that 10, you get the darker pink, not purple color. And when you do a certain titration, for example, like ones that you've done before, perhaps some vinegar and some sodium hydroxide, the equivalence point is, basic in this 8-ish range, which is why they usually have told you or yelled at you while you're doing titrations, stop when you see the lightest color of pink that will persist. And what they mean by that is if you do that and you kind of stop when you first see that hint of pink that your eye can see, you will probably be in this range of 8.3, 8.4, somewhere in that ballpark, mid-8s. And that probably also means that you are very close to the equivalence point. The reason they tell you not to go dark, super dark pink, because again, if you really did overshoot it, really, 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 really by a lot, that's going to send that pH way over here, which means you probably have added too much base in that case, and you're probably past the equivalence point. Although we did talk about the idea that if you really only passed it by a little, you probably would still be okay, because again, the equivalence point's here, and it does go vertical as you reach the equivalence point, which means you don't really have to add a lot of volume to see a big jump in the pH. And that's why, again, sometimes you will see that big jump in pH in terms of color when it goes from like one drop from barely any pink or no pink to like super dark pink. And you'll see that jump because you only added one drop. But again, you don't have to add a lot of volume to change the pH a lot. So even though you only added a little bit of volume, the pH changed a lot. And indicator-wise, the color changed a lot because of that. So again, like I said earlier, if you're doing it kind of drop by drop as you approach the equivalence point, which you most likely would be, and even if the color really went kind of really dark, you probably would be okay. No, it probably will. It will still sort of maintain. It probably would still maintain the pink color. So the question is, would it turn clear if you pass 10? No. For example, if you ever did the titration curve, well, maybe you haven't. You wouldn't do a titration curve probably in 1A, but if you did it and you continuously add, typically like the experiment you're going to see today, although they don't use indicator in the experiment, but I do teach at places where they do use indicator. If you do that and it gets up to like a pH of 12, it's still going to be pink at that point. So sort of the range that we see here on these guys are in general in terms of the indicator. The range is sort of an effective range for you to visually sort of see a color difference. So at some point, once you get kind of into that 10-ish range or before the 10-ish range, you know, there's really no distinction, right, between, oh, I think that's like a dark pink, but I think like this one's maybe a little darker pink or not. So you lose really that ability to have a good, clear distinction between sort of where you're at in it. And that's why on most of these, you want to choose an indicator where you'll actually see that color change. You'll be able to see that distinct color change to signal to you to stop the titration. But again, if you get sort of to the end of the range there, it's going to probably maintain that color. Even if you happen to go past the technical range of it, it will probably still stay that color at that point. Yeah, so typically in a acid-base titration, or what most people, if you took the first semester of chemistry, which I'm assuming all you did since you're sitting here in this class, right? So most of the time in most colleges I've ever seen, they always do this titration experiment. They give you some vinegar, right? And you do it with sodium hydroxide. And really vinegar is acetic acid. And acetic acid, as we know, is a weak acid. So again, in that type of titration, you have the sodium hydroxide, and down here you have your acetic acid. And you would put your indicator in, and usually you would use something like phenolphthalein, which is this guy here, I think. Yeah. And you would continue to add the sodium hydroxide to the acetic acid or the vinegar, and you would look for typically the first sign of pink that persists even after you mix it, and it stays. And you usually want to go for, the ideal thing is the lightest, like it's so light you need to take like a white piece of paper and kind of put it underneath it to see the tinge of pink. And what that usually will indicate to you is you should be near the equivalence point. Because in reality, the equivalence point in that titration there, maybe like 8.7, 8.6, somewhere in that ballpark. And because the early part of our indicator here, as you can see, is essentially colorless, we typically want to get it to the first shade of pink. And it's really the pink is for us to visually be able to see it, to know to stop. And that lightest pink that we could get would put us usually in the right pH range for the equivalence point. So you not only want, obviously, to choose an indicator correctly, you want to choose one where the actual changing part of that indicator is near your equivalence point again. So it's that visual stop that you should. Now, to sort of answer your question a little bit more, that when we're talking about when it turns pink, that is specific to using phenolphthalein as the indicator, because phenolphthalein, as you can see from the picture, kind of where I put the line, it goes from kind of colorless to pink. Obviously, if you use, say, this indicator here, which I can't really see what it is on my screen, but the writing is too small. When this would change color, it goes from a more yellow to greenish to blue type color. And maybe your equivalence points in that kind of greenish area. So if you were doing that type of titration, you would want to stop probably when you kind of see that first appearance of like green. So the colors of the indicators won't always be sort of colorless and pink. Again, that is sort of specific for phenolphthalein, and usually use that as an example because that's kind of the most popular indicator used in a lot of places. But again, if you choose a different indicator, there will be different colors associated with those. And obviously, it would change from one color to the next. So one color has more of the acidic side of the range, and one has more of the basic side of the range. And again, what that means is, you know, pH-wise here, this is all basic really, right? 8.3 to 10. But, you know, this side here, you know, is heading towards sort of the acidic neutral side is more colorless. And then as you transition really into basic pH, it turns pink and stuff. Other questions on that? So here's a table of some indicators and their color in acidic and basic solutions. And why don't you take a second and decide what indicator or indicators would be good for this type of titration, which is very similar to the titration we just did that problem on. So take a moment or two and think about which one are ones. I shouldn't cut myself off. Which ones are ones you may choose to be a good indicator for this type of titration. Okay, so when we're trying to decide what would be a good indicator, it's really good to decide what you got going on. So our HNO2, as we saw in that previous problem, definitely is a weak acid, and KOH is a strong base. So again, this is why it's important to understand those titrations that we talked about, because when somebody tells you, hey, you're doing a titration of a weak acid and a strong base, you should know right off the bat, when you reach the equivalence point, it should be basic. And you know, no matter what the situation is, it will be basic, just like we saw in the calculation that at that point, the only thing that we have left is a salt that will go through hydrolysis. The salt that goes through hydrolysis will produce hydroxide, and we know that the pH should be basic. So what does that mean in terms of the indicator? Well, if I look at the pH range on this list, let's just say from here to start with, those all work over pretty much an acidic pH range, which means if I decided to do my titration and use thymol blue as my indicator, which is the first one on the list, which changes color between a range of 1.2 pH and 2.8, this side being more red and this side being more yellow. Clearly in my titration that I am doing, my equivalence point is not going to happen until it's basic, which means if I dump my thymol blue in there, I'm going to kind of be yellow all the way through at that point, right? Because it's going to turn yellow in that like 2.8-ish range, or maybe a little before. And at that point, I've already seen a color change, and I am clearly nowhere near where my pH should be. So those all here would be not the greatest choice because of that. This guy, you may say, well, it gets into the basic range of like 6 to 7.6. Again, at 6-ish, and that side, it's yellow. And it is blue on sort of this end of the range, which means if you did your calculation, which you could do a theoretical pH at the equivalence point, you would probably see again that it is probably 8-ish. So for example, I think the one that we just did, the equivalence point pH was like 8.02, for example, which in that titration would not be good to use this indicator as well, because again, around 7.6 or maybe slightly before, I have already changed from yellow to blue, and I have now no distinction when I get to say 8.02 where that is, right? So the color change has occurred way before, maybe not way before in this case, but definitely well before my equivalence point. So that probably would not be the best choice either because of that, which means these two here, our good friend phenolphthalein, which works at 8.3 to 10, gives us probably a pretty good range of change. So for example, if we use the number we did in the calculation at 8.02, again at 8.3 to 10, kind of colorless to super pink at this end, but there is that gradual change from colorless to kind of light pink to darker pink. So if our equivalence point was 8.02, this would definitely be a case where we would want to go the first shade of pink that we could see and stop, because that should still put us around the 8.3 level or 8.4 level, which is, you know, a little off of our calculated pH at the equivalence point, but still in the ballpark. And the creosol red might still be good as well, again at 7.2, which is slightly basic, to 8.8 would cover us. So you might be able to see a change between yellow to red in that case as well. So out of this list, the last two would be okay choices in terms of indicators. Again, they both work in sort of the basic range where we see a change in color, and they would be a good choice to use as an indicator. Any questions on sort of that that logic there? So as you can see, creosol red and phenolphthalein in this case would be a good choice. By the way, the 8.2 is specific for the numbers we had in our titration. Like I said, if you were doing a real titration, you know the molarity of everybody when you start. You could probably do a rough calculation of what you expect the pH to be in terms of the equivalence point, and then you could obviously choose from a list, if you had it available to you, one where you would hopefully see a change in color. Any questions on indicators? Okay, so obviously you need to know indicators, a little bit how they work, and you know, how to pick the right one. You don't have to memorize, you know, the ranges at which they work or anything like that. So for example, if you had a question, a chart such as this might be provided for you, and you might have to pick out a proper indicator. Any questions on any of that? That should wrap up this chapter. Again, buffers, titrations, oh my, yes. A lot of stuff going on in this chapter here. And just a final note on titrations, and I might have mentioned it, but just in case I didn't, if you have a problem just like what we were doing previously, where there's like, you know, part A, part B, part C, sometimes people mess up because they think they should kind of use the information from part A, like you added 25 milliliters, and then what is the pH after 50 milliliters is added. So sometimes people will kind of add those together and go, oh, I did 50 and then 25 in the first one, so I got 75 total. So usually in a titration problem, unless otherwise stated, if there's multiple sort of parts where they're like, what's the pH after 15? What's the pH after 25? There's sort of individual type problems. So what I mean by that is, if the first question was, what is the pH after 15 milliliters of sodium hydroxide is added? What that means is you open up the burette, add 15 milliliters, close the burette, and what the pH would be at that point. If part B was 25 milliliters, what that means is you would start at 0, open up the burette, let it flow down 25 milliliters, and what the pH would be at that point. So going in like another 10 milliliters from A to B, but not adding them together. So if you were doing, for example, and it does depend on the type of titration that you're doing. So obviously if you were doing something that's a strong acid, strong base titration, you would expect the pH to be 7 right at the equivalence point. So you would want something that perhaps changes color in that 7-ish range. I sort of scribbled over on some of those stuff, but I think, you know, for example, bromothymol blue, if I'm not mistaken, 6 to 7.6, right? So that might be a good choice for that type of titration. Maybe even creosol red would be a good choice. Honestly, people will use phenolphthalein for that type of titration as well. Not really the greatest choice, but if you stop it at that first sign of pink, you are probably a little past the equivalence point, but you're still in that neighborhood. But a better choice for something like that would probably be something like bromothymol blue that's on that list. Again, before I crossed it out, I think it was like 6 to 7.6. So you probably would be able to see that color change occur near a pH of 7, which is what you would expect. And obviously the last type of titration that we talked about would be the strong acid weak base titration, which, remember, when you get to the equivalence point would be acidic. So depending on what you're titrating and what your theoretical pH would be, these guys here would be probably one of those would be a good choice to use for that type of titration. Again, because in that case, the equivalence point should be acidic. So it's really dependent on the type of titration you're doing, because for each of those, you should understand, where in terms of pH the equivalence point would be. And if you really wanted to super zoom in on it, you could do like a theoretical calculation based on your actual acid or base or whatever you're using, and you could get kind of a theoretical value of what your equivalence point pH should be, and you really could probably zone in on a very, very good choice in terms of the indicators. So sometimes people think with acid-base indicators that, phenolphthalein, like my pink shirt here, phenolphthalein is like the choice to use, right, in every situation, but it's really not. It just happens to be in most titrations the students do. Like I said, it's cheap to go get vinegar at Costco, right? And using vinegar and sodium hydroxide, that's usually a very popular titration that's used. And that equivalence point is usually in that 8 point something range. And that's why most people have only used probably phenolphthalein as their indicator. Other questions on that? All right, so that should wrap chapter 15. Then we're going to go off to chapter 16. Again, the notes should be up online if you need them. So if you need a couple of seconds or so to go grab those, you can. While I also go try to figure out how to get the next one up here. So give me just a sec to click around. Okay, we're going to roll into chapter 16, and we're going to talk about another type of equilibrium expression. And really this deals with specifically, and really the only part of the class that deals mainly specifically with those qualitative analysis type experiments we're doing, and that is Ksp. Now, if I'm not mistaken, I'm going to try to remember, but I believe chapter 16, I think there's 3 sections. The last section involves complex ions, and we're not going to do complex ions right now. We're going to come back to it a little bit later on in the semester. So after we talk about sort of complex ions, transition metals, I apologize, but I used to be like chapter 21. It might still be, maybe it's 22, somewhere in that ballpark. We'll get to that chapter, and then we'll circle back to the third part of this chapter, which is complex ions and the calculations that go with it. So if you're looking through your book or something like that, you will see, I think, a section that involves complex ions and sort of the calculations. Kf is known as the formation constant. And again, we're going to skip it for now, but we'll come back to it a little bit later on after we talk about kind of complex ions and how to name them and stuff like that. So what we're going to talk about here is Ksp. And Ksp is the solubility product. That is what that is. Should probably get a pen. Let's try that again. Try that button. There we go. So SP is the solubility product. And Ksp is just an equilibrium constant. And as odd as it may sound, it's an equilibrium constant for things that are insoluble typically. So these are typically for things that are insoluble. I learned how to spell there. And this is really where sometimes, again, if it's been a little while for solubility rules, you may want to review them. It may be helpful, although, you know, you probably be able to figure out most things, even if you have just a casual understanding of the solubility rules. You'll be able to sort of figure out what you need, but probably a good idea to have some understanding. So again, if it's been a little while for the solubility rules, make sure you kind of refresh yourself on them. And again, it will be kind of helpful for you here in this chapter. So the way that these guys are written, because they are typically insoluble guys, is the reaction for these guys are usually always written the same way. We typically have solids only on the reactant side, and we have aqueous ions on the product side. So when we do write these Ksp expressions, as we will see in a sec, it is typically only the products included. It is normally like a normal equilibrium expression, products over reactants, but in pretty much all cases here with Ksp, the reactant side is just solids. So they're usually never included. So usually Ksps will just look like the products only. And let's take a look at that. So for example, if we take silver chloride will break apart into silver ions and chloride ions. So again, if we write our equilibrium expression, we would take products over reactants. And here again, our reactants would be a solid. So it would just be our products, which is the concentration of silver times the concentration of chloride. So that would be our equilibrium expression. And again, that is what is known as the solubility product. And here's a few more examples of those. Again, we do everything just like we've done before. Again, products over reactants. And you can see in each of these cases, on the reactant side, they're all solids. So we still do exactly what we always do with equilibrium expressions. We have our coefficient of 2. It finds its way over here. Coefficient of 2 finds its way over here. A 3 and a 2. We cube it and we square it as well. So you may say to yourself, all right, well, they made me learn all those solubility rules, and it tells me that silver chloride is insoluble always. So why would there be ions? And the reason for that is, even if something is technically insoluble based on the solubility rules, there is some degree of solubility with everything. So a little super small amount will still dissolve, but a vast majority of it will not. And because it's still a little bit of it is able to dissolve, even though it's technically insoluble, it is able to set up these equilibriums. And as we will see in a second, that is why when we see the value for KSPs, they are typically very small values. And that's because they are essentially insoluble. But everything, like I said, has some degree of solubility to it. And as we will see in this chapter, there's a lot of factors that affect solubility. So there are things that, even though technically speaking, based on the solubility rules, like we see here with silver chloride, that we tend to think always, in all cases, no matter what the deal is, it's always going to be a solid. And as we will see in this chapter, that's not always the case. There's a lot of factors that are important as to whether or not you would see the solid form or not see the solid form. And some of those, as we will see, is things like concentration is really important. Things like pH is really important. And that's why when you read through those qualitative analysis experiments, there's a lot of steps where you play with the pH, change the pH, and so forth. And that has a lot to do with allowing things either to dissolve or allow things to come out as solids. And so there's a lot of factors involved as to whether or not you would actually see something sort of follow the solubility rules. So sometimes in the first part of the class or the first semester, we always think of them as, definites for sure. Hey, I look at my little solubility list, my solubility song. I don't know. Some people have a song. And it's always 100% always going to be that. And it's not always the case. There's a lot of factors that actually can affect things like solubility. Now we can use our Ksp and our good friend Q. So if you remember, Q here is the exact same Q that we saw everywhere else. Q again is calculated the exact same way as you would calculate Ksp in this case. So in most cases, so for example, if we wanted to calculate Q for the top guy, Q would equal the concentration of silver times the concentration of chloride. And we could use Q kind of similar to what we used it before to help us determine whether or not we would expect a precipitate to form or not. So if we calculate Q and it is less than the Ksp, we will have an unsaturated solution. So a reminder that these reactions are pretty much written like this: solid on the left-hand side, aqueous ions on the right-hand side. So again, going opposite the way that arrow is pointing, if Q is less than the Ksp, that means we're going in this direction, and we would expect aqueous ions being formed. And an unsaturated solution means that you have not hit the saturation point, and the saturation point is the point where no more solid will dissolve. So you haven't hit that point yet. So we would expect no precipitate to occur. So if you calculate Q and it's less than the Ksp, you would expect no precipitate. If you calculate Q and it's equal to the Ksp, you pretty much have hit the saturation point. You're at the saturation solution or saturated solution. And what a saturated solution means is you are exactly at the point where 100% of what you put in there will dissolve. And you're also at the point where if you decide to put just a little bit more in there, no more of it will dissolve at that point. And that's basically what a saturated solution is. And that brings us to if Q is greater than Ksp. If Q is greater than the Ksp value, that means that you have a supersaturated solution. And that means that you would expect to precipitate. Definition really of a supersaturated solution is one where you have too much solute dissolved in the solvent. And it typically does not like that. And the solute likes to come out of solution and make a solid. By the way, a solution is made up of two parts, right? The solute, which is the smaller part, and the solvent, which is the larger part of the solution, right? And again, typically if you take a solid like sodium chloride, dissolve it in water. The sodium chloride is the solute, the water is the solvent. Usually the name of the solution is the solute. So if you calculate Q is less than the Ksp, no precipitation you would expect to occur. If you calculate Q and it's greater than the Ksp, you would expect precipitation to occur. Any questions on that there? Here's the values in those table here, and I personally can't see it very well on my screen, but you have a similar table in your book. I think this might be from an older version of your book, but I think it's down in chapter 16, I would assume. But if you look, or you can see sort of those numbers, what you will see pretty much when you look at all these numbers is they are all very, very small values. So Ksp values are usually very small. So what does that mean? As we've been talking about, what that essentially means is since those reactions are solids on the left-hand side, aqueous ions on the right-hand side, if my K value is small, that means when I reach equilibrium, I mainly have reactants. Which means in this example, if I mainly have reactants, I mainly have a solid, which is why when we look at these things on this list, these are the things that we typically associate with those solubility rules as being insoluble. So you can see right about, for example, here, these are like our group 1 guys, right? With the bromides, silver, lead, and mercury 1. Remember, for example, your solubility rules, your chlorides, bromides, iodides. They are typically soluble in everything except silver, lead, and mercury, basically. And that's mercury 1. And those guys are typically insoluble. But again, if you look at all these values for these Ks, they're very small values, which implies that you pretty much do have mainly solids at equilibrium. And again, even though something is technically insoluble, as we've been talking about, there is still that small degree of solubility that occurs with everything. So let's talk about sort of problems that we do, or how we approach sort of problems that involve solubility. And there's really sort of 2 types of problems, and sometimes 2 types of solubility that we're asked to solve for. One is the molar solubility, and that is the number of moles of solute that's dissolved in 1 liter of a saturated solution. I don't know if that's a fancy way of saying it or not, but basically we're talking about the molarity, right, which is moles per liter. And then sometimes people will just talk about solubility in general, and that is how many grams per liter you can dissolve. So that's basically how many grams of that substance you could dissolve in, for example, 1 liter of solution. And there's really 2 ways that these problems a lot of times take shape. They oftentimes will give you the solubility of the compound. They may give you the solubility in grams per liter, milligrams per milliliter, moles per liter. They may give you some type of solubility of a compound. What you need to figure out is what the molar solubility is, so the moles per liter, if they don't give it to you in that. Then they will have 2 ions, right? You'll have a cation and an anion, positive, negative guy. You need to figure out what the concentrations are of each of those ions, and then you could actually calculate the Ksp by putting those concentrations into the Ksp expression. Now, the other type of sort of Ksp problem that you'll come across is one where the only thing that you're given is the Ksp value. So they'll tell you, hey, silver chloride has a Ksp of whatever the number is. What is the solubility of silver chloride in water? And that's pretty much all they give you. So in a case when they do that, you really have to do our favorite thing at this point, a nice table. Yeah. So you do have to do an ice table, usually in a problem where they give you the Ksp and no other piece of information. The ice table is done just like all the other ice tables that we've done. There is a slight few different things that are done here because it's solubility, and we'll talk about that in just a second. But basically, you'll be able to find the solubility of the compound, and you can find the molar solubility, and then obviously the grams per liter if you wanted to of each of those. So these are the 2 common type of problems that you come across with Ksp. Truth be told, you could do an ice table on both of them. The first type of problem, you don't really need to do an ice table, but sometimes people might like to do it so they don't mess up on certain parts of the calculation. And I'll kind of point those out as we go through it. There's some very common things that occur in these type of calculations that confuse people. And what we're talking about is, and we'll see in a second, you might have to, multiply by 3 and also cube it. And people think, well, do I have to multiply it by 3 and then cube it, or just cube it, not multiply by 3? So there's a lot of things that sometimes, even technically, if you don't have to do the ice table, it sometimes can be very helpful for you. So that's a lot of talking. Let's talk about an actual example. So let's take a look at this example here. And we're going to talk about how you could do this example. And I'm going to show you sort of 2 ways to do it, and sort of show you that, you don't necessarily have to do an ice table here, but it might be helpful for you to understand sort of what's going on. So the first thing that you want to think about is this guy here, which is silver phosphate. And we know a couple of things about it. Because we're looking for the Ksp value, that automatically probably will tell us that it is going to be a solid here, because pretty much Ksp is for things that are solid that breaks apart into ions. So that's sort of how we know it's a solid. When it does break apart, it is going to break apart into 3 silver ions and a phosphate ion. Now we can write our Ksp expression here, and that would be the concentration of our silver. We would have to cube it, again for the coefficient that's here, and we would times it by our phosphate, which the coefficient is 1. So obviously we don't have to do any type of cubing. Now, you technically don't have to do an ice table, but I'm going to demonstrate the ice table here because this is very much how an ice table will look for problems where you definitely do have to do an ice table. So the ice table is going to be done very similar to what we've done before. So in this particular case, what a normal ice table would look like is the solid here we're not going to worry about. We normally would say 0 to start with for both of these. Okay. The change part is going to be just like normal. We're going to assume that this reaction is heading towards the product side, which means minuses would be on the reactant side, which in this case, we don't have anything to worry about because it's all a solid. And the positives would be on the product side. Now, it truly doesn't matter what I'm going to do next in terms of the letter, but most people, when they do some type of solubility problem like what we're doing here, up until this point for our ice tables, we use X's to represent the change. Usually when people do Ksp problems, they decided, probably because they were bored of X's, they decided to use a different letter. And they actually use the letter S here. And this would be plus 3S and plus S. The S works the exact same way as the X did. It kind of means the same thing. But what it also means in this type of problem is the S actually stands for the molar solubility, which again is a fancy way of saying molarity. Yeah. So when we see the S in these type of tables, which is very common to use, and like I said, if you like X, you could continue to use X if you want, but people will commonly use the S's here. And that represents basically the molar solubility, which means when we come down to our equilibrium, we have 3S and S. And what we normally would do in this ice table is take that equilibrium line and stick it into our Ksp expression, right? So the Ksp would equal 3S cubed times S. And normally, if we did have the Ksp value given to us, we would actually solve for S. And if we solve for S, that would be the molar solubility of what we're looking for. So in a problem where you definitely do need to do an ice table, this is essentially how the ice table looks. It's very similar to our normal setup, again, except that we use S to represent molar solubility. Any questions on that so far? Now, in this particular problem, we're actually looking for what the Ksp is, and the piece of information they actually gave us was that the solubility is 1.6 times 10 to the minus 5 moles per liter. Moles per liter is molarity, which means technically in this problem, they gave us that the S is equal to 1.6 times 10 to the minus 5 molar, which means that is this S and that's that S, which means we could actually solve for it by taking 3 times 1.6 times 10 to the minus 5 cubed times 1.6 times 10 to the minus 5. And if you do all that carefully, maybe. So 3 times 1.6 to the minus 5, we then need to cube it and times it by 1.6 to the minus 5. That gives us 1.8 times 10 to the minus 18 as our Ksp value. Any questions on that? So when I say in this particular problem, you didn't really need to do the ice table, that is because if you understand molarity and how molarity works, you basically can figure it out just from the concentration. So again, if you remember molarity, when this breaks apart into these guys, if this guy is 1.6 times 10 to the minus 5, this guy should be 3 times 1.6 times 10 to the minus 5, as it's a 1 to 3 relationship. And it's a 1 to 1 relationship between the whole thing and phosphate, which means this guy would be 1.6 times 10 to the minus 5. If you understand that, you then can just go directly into here, right? With those numbers, which effectively is what we did by doing it with the ice table, but you don't necessarily have to do the ice table in this case. You could just get those values and go in there. The benefit of the ice table is sometimes, and very, very common, people forget to multiply by the 3, or if they multiply by the 3, they somehow think, I don't need to cube it at that point. So there's a lot of that occurs with these problems with people. They like do one thing and figure, well, no, I don't need to do something else, or maybe I need to do it or not do it. So there's a lot of that occurs where they either forget to multiply it by a number, or they forget to square it, cube it, or stuff like that. So sometimes if you just do the ice table no matter what, it's sort of visually you can kind of see the mathematical approach that you need to do. Any questions on that there? Okay, we're going to stop there, looks like. And so today we're going to do the titration experiments. I think we're gonna do both. So we're gonna watch the videos for both. They're not very long videos. And I think they will be due, the experiments will probably be due tomorrow officially. You can turn it in today if you want. But I don't think there's very much kind of pre-calculations and stuff like that you had to do, like in the buffer experiments and stuff like that. So it's just sort of watching the titrations, and you'll get the values and stuff that you need. So I think we'll talk a little bit about the titration experiments, and then I think we're probably just going to kind of do both today, the 8 and 9. And like I said, I think I'm going to make them due probably tomorrow officially, and I'll give you a little extra time to do that. But if you knock them out today, you could obviously turn them in today. So that's the tentative game plan. So make sure you have sort of available to you the stuff for experiment 8, like I said, and then also 9. So that should be the monoproduct titration, and then also the diproduct titration. Any questions on any of that? So again, make sure you type here into the box, and we'll start about 3-ish in the lab one. And again, we're going to try to take care of both of those today, I think. All right, I'll see everybody in about 10 minutes or so.